Welcome back to the lecture series in bioelectrochemistry. So, we have finished 10 lectures as of now, and the last lecture were concentrated on, last couple of lectures were concentrated on Nernst equation. So, though in the last week you are supposed to switch over to the different kinds of electrode, but we rather is moving towards that topic much more slowly. So, the reason being, I am again reiterating the point that I wish your fundamentals should be very clear. Now, coming back to the Nernst equation and the reaction when we describe. So, if you realize, if you have two different electrodes, say A and B, cadmium and silver. So, there are two different level of equilibrium which are getting established. So, a galvanic cell produces electricity because the cell reaction is not at equilibrium, but once it reaches equilibrium, automatically the voltage will become 0 and nothing will flow, and that is what precisely happens in a battery when we say this common word, the battery drains out. Battery is no more performing the reaction. So, here there are batteries which are rechargeable. Essentially think of it, what is happening, just put your logic in place. So, you have say current flowing from A to B or B to A whatsoever, okay, because the reaction is not at equilibrium. So, once it reaches equilibrium, the voltage across them becomes 0. So, there will not be any further flow of because it has reached the equilibrium. Now, if you reverse the polarity, so what you essentially did, so there are chemical reactions which led to the electricity production. Now, if you put electricity, then you can recharge it back by allowing the chemicals to maintain another new set of potentials. So, essentially you can reverse, and that is where comes the whole concept of rechargeable batteries. So, this is just a deviation from our normally, but course of study. But what is important for you to understand that there are two sets of equilibrium which are being set. So, say for example, you have electrode A, you have electrode B. Now, electrode A is in equilibrium with its own surrounding. Whenever if you remember that when we measured that if you put a hydrogen probe there in sync with that. Similarly, electrode B is in equilibrium with its own reference electrode, and then E and B has a different set of equilibrium among each other. So, individual cells. So, here we call each one of these as individual cells. So, just to put it something like this, we are into week 3. This is lecture 11, week 3. This is first lecture of week 3, lecture 1, W3 L1. And what I am trying to tell you is, so essentially what we are doing today is we will be touching upon the relation between E0 and the equilibrium constant. Okay. So, what I highlighted just now is that a galvanic cell produces electricity because the cell reaction is not at equilibrium. Okay. Galvanic cell produces electricity because the cell reaction is not at equilibrium. Reaction is not at equilibrium. So, this is one of the fundamental thing. The potentiometer allows negligible current. So, the concentration of the cell remain unchanged. If we replace the potentiometer, say for example, you have this potentiometer which is connecting to say cell. So, when you are connecting it with a potentiometer, there is a negligible current which is flowing through, okay, allow negligible current. So, the concentration in the cell remain unchanged. If we replace the potentiometer with a wire, say for example, you are removing the potentiometer and allowing the electrons to flow through. Okay. If we replace the potentiometer with a wire, there would be much more current and the concentration would change until the cell reach the equilibrium value. Okay. At that point, nothing would drive the reaction and E would become 0. Okay. So, when a battery which is a galvanic cell runs down to 0 volt, the chemicals inside have reached equilibrium and the battery is dead. So, this is one concept which I wish you should understand. The second thing what is important here is, let us relate the E for a whole cell to the reaction quotient Q. Okay. So, we are trying to relate E and Q, which is the reaction quotient. Reaction QUOTIENT, reaction quotient. Okay. So, now say for example, on your right hand electrode, so let us write down both the reactions. So, on your right electrode, you have the reaction like AA plus NE C. Okay. Whereas, on your left electrode, you have the second set of reaction going DD plus NE B. Okay. Now, if you write down the Nernst equation for us, so now this is the right electrode. So, this is your 0 plus, this we have already talked, 0 minus. Okay. Now, at equilibrium we have already talked about E is equal to 0. Now, the Nernst equation for this will looks like something like this. We know that E is equal to E plus minus minus. So, this is your E minus term, okay, and this is your plus term. Now, if you write this equation, it will become something like this. E is equal to 0 plus minus. So, this is minus 0. I am not deriving it further because you already know this, divided by number of electrons, log the base 10 C. So, essentially I am writing this part, this term and this term is coming there, A, okay, minus, let's put the big brackets there, okay, minus, you have the second term which is the left electrode now coming into play, which is E minus electrode, which is E 0 minus. Now, here is the minus term. So, this is the whole term by the way, minus 0.05916 divided by n log So, you have the other reaction as this is BB and this is DD. Okay. So, you have DD and you are closing upon the bracket. Okay. So, this is what the Nernst equation will look like. Now, we know that log A plus log B is equal to log AB. This relation we are aware of. If you know this relation, so essentially your this term and your this term are basically very similar to this. So, we can really multiply these two terms. So, if you rearrange this whole thing, so then the equation becomes E is equal to E 0 plus minus E 0 minus, which whole terms is essentially is your E 0 minus, I am putting additional brackets so that you do not get confused, 0.05916 divided by number of electrons log C d d divided by A B B. This whole term is your Q. Okay. So, now if you write this term, this becomes your E 0, which is standard potential, okay, minus 0.05916 divided by n log Q. Okay. Now, simplifying the equation. So, in a special case when E equals to 0 and Q is equal to K, that is where you are trying to find the equilibrium constant, because mind it, these are different kind of reactants which are involved in this whole process. So, what you are getting in that situation, you are finding E 0 from K, that makes it E 0 equals to 0.05916 divided by n is equal to log K. Similarly, finding K from E 0, finding K from E 0 is equal is K is equal to 10 n E 0 0.05916, and all these reactions are happening at 25° centigrade. Okay. So, this is where we are establishing a relationship between E 0 and the equilibrium constant. This is the relation which I wanted to establish with you people. The next thing what I wish to establish is cell as chemical probe. So, here when we talk about the cell, we essentially mean the half cells as chemical probes. What does that mean? I am coming to that. So, I told you that equilibrium has to be established at two different levels. Equilibrium has to be established on the half cells, and equilibrium has to be established between the half cells. Okay. So, we can understand that any of these parameters, if it is unknown and if you know the other three parameters, we can figure out what is the fourth parameter. Just keep it in mind. So, let us enumerate what all I am trying to highlight here. So, the point 1, it is essential to distinguish two classes of equilibria associated with galvanic cell. Okay. It is essential to distinguish two classes of equilibrium associated with galvanic cells. Okay. So, what are those? So, the first one is equilibrium between two half cells. Equilibrium between two half cells. Point 1, and second one is equilibrium within each half cell. Equilibrium within each half cell. So, now what I will do, use this opportunity to explore how this could be used to find out hydrogen ion concentration, H plus ion concentration. Okay. So, let me draw a cell. So, and keep another thing in mind, if a galvanic cell has a non-zero voltage, then the net cell reaction is not at equilibrium. We said that the equilibrium between the two half cells has not been established, and if we allow the half cells to stand long enough to come to chemical equilibrium within each half cell. Okay. So, keeping that in mind, let us draw the cell. So, here is one cell, here is the next cell. Okay. So, these two cells are connected with a salt bridge. You have a salt bridge connecting them, and you have a voltmeter connected there, and on your right hand side you have silver electrode, which is AgCl electrode. Okay. And this is in 0.10 molar KCl. Okay. This is Ag. Okay. And this is your salt bridge. And here you have the typical hydrogen electrode with a platinum, and you have hydrogen at 1 bar, right. And on this side what you have. So, if I put the cell reaction, this is platinum solid, hydrogen at 1 bar, and this is balancing with CH3CO2 H 0.050 mole multiplied by CH3CO2 Na with 0.005 mole. So, which is essentially a buffer. This is what is buffering it. And you have the double line showing the other side, the right hand side of the reaction, which is chloride minus 0.10 mole with AgCl solid, Ag solid. So, this is what the reaction looks like. Okay. So, now we allow the half cell to stand long enough to come in chemical equilibrium within each half cell. For example, on the right hand side what you are having is AgCl solid, it is coming in equilibrium with Ag plus aqueous plus Cl minus aqueous. Okay, is at equilibrium. So, this is where it is reaching an equilibrium. On the other hand, the other side, it is simply on the other side what you are having is CH3CO2H is coming in equilibrium with CH3 CO2 minus plus H plus. This other left hand side is also at equilibrium. Okay. So, both the reactions at the individual at within each half cell is at equilibrium. Okay. The redox reaction for the right half of the cell, which is, if you see on this right half of the cell, the redox reaction is something like this. If I write the redox reaction on the right hand side, it will be AgCl solid plus electron, making it Ag solid, chloride minus 0.1 molar, and E0 plus is 0.222 volt. Okay. But what is the reaction in the left cell? The only element we find in 2 oxidation state is hydrogen. So, we see that hydrogen bubbles into the cell if you look at it carefully. So, what you are observing? So, there is an hydrogen bubbling which is happening, and the only element we find in the 2 oxidation state is hydrogen. Okay. And we also realize that every aqueous solution contains H plus. Therefore, hydrogen is present in 2 oxidation state, and the half reaction can be written as, so now I am writing the half reaction of the left hand side, which could be written as 2H plus aqueous, we do not know how much is the molarity, plus 2 electron, giving rise to hydrogen, which is gas 1 bar, and E0 negative is equal to 0. This is what we are assuming. So, what we do not know is what is the concentration of this H plus ions. So, the net reaction is not at equilibrium because the measured voltage is 0.503, and so the measured, so this is what is it. So, the net measured, what we are measuring is out here, if you look at it, this value, if you look at it carefully. So, then this value is plus 0.503 volt. So, it means whenever this is showing this value, which is this side is negative, this side is positive, it means the cell is not at equilibrium. So, okay, that cell reaction is not at equilibrium because the measured value is 0.503 volt, not 0 volt. So, the Nernst equation for the cell reaction will be, now if you write the Nernst equation for it, it will be something like this: E is equal to E plus minus E minus. Okay. If this is the case, then 0.222, which is on the silver chloride side, 0.05916 log of Cl minus, minus, here it is 0 minus 0.05916 divided by 2 log Now, what we do not know here is this term. This term is unknown to us. After inserting the known quantities, we discovered that the only unknown is the H plus. Okay. So, the measured voltage therefore allows us to find H plus. So, now what you do out here, you know this, okay. This is known to us, right, which is your 0.503 volt. This is experimentally you are measuring it, because this is not at equilibrium. So, if you insert this value, this is what I am trying to tell you, insert this value there and then you pull down this whole thing 0.222 minus 0.05916, then you have log of 0.101 minus 0 minus 0.05916 divided by 2 log of 1 . Okay. Then you will calculate that H plus concentration is equal to 1.8 10 to the power minus 4 mole. So, you realize this in turn allows us to evaluate the equilibrium constant for acid base reaction that comes to equilibrium in the left hand side. So, you are realizing that based on this, you can really take it to the next level, where you can calculate is equal to CH3 CO2. So, if you remember on the left hand side how the concentrations of these were shown, CH3 CO2 H, and if you insert the values now, this is what you are going to get. And that brings us to 5. So, if you realize that we now have a probe to measure the H plus ion concentration, proton concentration. Using this type of cell, we could determine the equilibrium constant of acid dissociation and base hydrolysis on the left cell. So, you realize that these kind of cells could come very handy when you have to translate between a chemical reaction and the electrical output, and vice versa, electrical output and a chemical reaction. So, here see, it is a very simple thing, where if you know the redox reaction, if you can build up the redox reaction out here, what you did, you really can figure out how to measure the concentration. So, what we essentially did, we measured this value which was unknown to us. So, this is how, it is a very simplest example. I wish you to go through it very carefully. This is how you measure, in a simplest term, in a very simple term, the different kind of analytes which are present. Especially here, it is the H plus ion concentration, which will tell you essentially this is, in a way, you are telling what is the pH, okay, which is H plus ion concentration. Is it acidic pH or is it a basic pH? Okay. So, I will close in here, and the next class we will be introducing some of the biomolecules. As of now, we have talked about most of it is the inorganic part. So, we will talk about the significance of E0 for the biochemist. Okay.